Welcome back. So, we were talking about the free field action before the break. The free field action is given by this expression in your green box, and the probability distribution, the normalization for the probability distribution we had worked out. It is nothing but a simple Gaussian integral. In fact, this distribution happens to be a Gaussian distribution, and the normalization factor is under root mu upon 2 pi, and therefore, the complete distribution is given by the expression in your green box, right. So, the generating functional we worked out. Generating functional is again can be explicitly worked out, can be worked out in closed form because of the simplicity of the distribution, and we have the generating functional as exponential of j square upon 2 mu. That is again obtained simply by a Gaussian integral. And this is the normalization that I just talked about, z0 of 0, and the value of z0 for j equal to 0 is equal to 1. Now, we recover the green functions from the generating functional. Let us see what we get. Remember, the generating functional is exponential j square upon 2 mu. So, g1 will be equal to the first derivative. G0 for you can check G0 is equal to 1 here. G1, if you work out, G1 is the first derivative of this expression of the generating function Zj, and the first derivative happens to be j upon mu exponential j square upon 2 mu. Put j equal to 0, this expression gives me 1 and this expression becomes 0. So, the net result is 0. In fact, you will see that all the odd green functions, odd point green functions vanish. Let us see what happens to G2. G2, when we work out, we take a second derivative of the generating functional, we get, on substituting j equal to 0, we get the expression 1 upon mu. The odd point functions will vanish and the even point functions will be given by this expression, and this is obtained from the general formula or the formula for the general even moments of the Gaussian distribution. So, G2n is equal to 2n factorial upon 2 to the power n factorial 1 upon mu to the power n, and all odd green functions will be 0. For the connected Green's functions, we have Wz is equal to square upon 2 mu. Remember, Zj is equal to exponential of j square upon 2 mu. Therefore, log of Zj is j square upon 2 mu, and therefore, the connected Green functions we get from taking derivatives of j square upon 2 mu, which gives us the following: C0 is equal to 0, C1 the first derivative, again if you put j equal to 0, you get 0, and C2 is equal to 1 upon mu. Remember, C2 is the variance of the distribution. And the field function, well, the field function is given by phi symbol of j, which is the first derivative of the generating function for the connected Green functions, and that when we substitute the value we get, that is j upon mu. So, the field function is given by j upon mu. Also recall that this field function is the expectation value of the field variable in the presence of the source term. Now, we come to interaction models. We have talked about the free field theory of the 0 dimensional QFT. Now, we talk about an interaction model of 0 dimensional QFT, where we have an interaction term in the action. If there is any other term than the quadratic term, we call the other term as the interaction term. Now, if we consider adding a constant to the action, it does not give us any new physics. Why it does not give us any new physics is because it can simply be absorbed into the normalization. For example, if I have instead of the action minus s pi plus say theta, then e to the power theta can be absorbed, theta or minus theta can be absorbed into the normalization factor. A linear term can be treated similarly. If you have a linear term, add a linear term to the action, what happens is by changing by shifting the origin, we can retain the Gaussian structure of the action, and therefore, it does not contribute to any new significant new physics. Now, what about a phi 3 term, a cubic term? Now, if you have a cubic term, this situation becomes interesting. This situation does become interesting, but the action becomes unbounded from below, because for negative values of phi, which are definitely permitted, for negative values of phi, this phi 3 term will blow up. And the action will become unbounded from below, and because the action will become unbounded from below due to the phi taking negative values, and therefore, phi cube taking negative values, the exponential minus s will become unbounded, and as a result of which the action does not lead to a convergent integral, and therefore, the phi 3 interaction or the phi 3 interaction in itself becomes a redundant exercise. However, one can definitely have a phi 3 4 theory. That means, you can have a phi cube interaction when you include a phi 4 interaction as well. We shall investigate a little bit about it in a later lectures, but for the moment, because we have because of this problem of convergence associated with phi cube interaction, the next candidate for an interaction term is the phi 4 interaction. Now, lambda 4 is an interaction constant, a coupling constant it is called, and we assume that lambda 4 is positive and is small, small enough to facilitate a perturbation solution to our problem. So, we have the exponential of minus s phi s interaction. Please note this, here the action is the interaction action, not the original pre-field action, is the interaction action. So, we have it exponential minus 1 by 2 mu phi square plus 1 by 2 lambda 4 phi 4. This is the interaction action, and this is the interaction action. So, if you simplify this, simplify this, we can split the exponentials, and we retain exponential minus 1 by 2 mu square mu pi square, and the other exponential we expand as a power series in lambda. The interaction term, that is this interaction term, we expand as a power series in lambda. Obviously, the normalization factor will also change. Once the interaction terms comes into play or comes into the action, becomes a part of the action, the normalization also changes. The interaction, the normalization in the case of the new action can be written in this form, this whole thing in this whole thing inverse. See, we have simply I have simply reproduced what was there in the earlier slide. This expression in the red box I have carried forward, and this expression in the red box I have reproduced here. Now, comes a very important step. The important step is, if you look at this expression, the summation is within the integral. In other words, first we are doing the summation and then we are doing the integral. But if you look at this, the next step, that is the step in the light green box, then the summation has been taken outside the integral. In other words, now what we are saying is that we first do the integral and then we do the summation. Now, there are a lot of technical issues associated with this transposition. It is not blatantly permitted, it is not blindly permitted, it is not universally permitted. It can only be allowed under certain specific circumstances, certain specific behavior of the underlying variables. Now, I shall come back to it, it will be a digression, but I shall address this issue in our current context at the end of this particular theory, zero dimensional theory, and we shall talk more about it. For the moment, we take it as granted, for the moment only, but we shall readdress this particular situation. We assume that we are assuming It is not a default option, please note this, it is not a default option, we are assuming that this is permitted. Now, if this is permitted, then things do simplify, then the integral, if you look at it carefully, the integral becomes a movement of the Gaussian distribution phi 4k exponential minus 1 by 2 mu, and this is nothing but the 4kth movement of the distribution represented by the PDF given by exponential minus 1 by 2 mu phi square PDF in the probability density function, and therefore that being the case, what we have is that the result is that this whole expression the this integral as a whole, this only the integral part on simplification, because it is it's an even movement of a normal distribution, it can be simplified, exact result can be obtained, and the exact result is 2 pi upon mu to the power 1 by 2 4k factorial 4 to the power k 2k factorial. This is the expression for this, the integral that I was talking about in the previous slide. The rest of the expression remains as it is for the moment, and it is retained here in the current form. Now, this is the expression for the normalization constant. Please note this. The expression in the green box is the expression for the normalization constant. Please note this inverse here also. Now, we work out the generating functional. Now, let us work out the generating functional. The generating functional for the interaction theory is given by this expression Z interaction J is n interaction, where n interaction we have just worked out, it is a normalization factor exponential minus. Now, we have a source term added in, source term included in J phi, and putting in the expression for exponential for the action that we worked out earlier, we get this expression, and now we have the additional expression of J phi here. The expression for the interaction action is given in the equation 1. So, the interaction action is given by equation 1 here, and if you take the exponential, we get this expression where we have expanded the perturbation or expanded the interaction as a power series as we have done earlier, and the Zj, the interaction generating functional is now given by this expression plus the additional J phi, which will help us to work out the green functions for the various orders. So, Z interaction J is what we have here. Now, again we have adopted this particular trick or this particular manipulation, I should say, that we have shifted the summation which is within the integral to summation which is outside the integral. As I mentioned, strictly speaking, it is not permitted by mathematics. There are certain requirements that need to be met, technical requirements that need to be met, and only then we can make this transposition, but we will get back to it. For the moment, we assume that this is permitted, and we made this substitution and we transposition, and we get this expression. Now, we are now going to simplify the integral. When we simplify the integral and for the first derivative, let us say we want to work out the first green function, first order green function, 1 point green function. We take the first derivative of the generating functional with respect to the source term, that is J. Now, when we take the derivative with respect to J, this J attaches itself to the exponential term, because there is no other J here in fact. So, this J attaches, and the integration is with respect to phi, and the derivative is with respect to J. So, you can take J inside the integral and it attaches itself, it operates on J phi and brings back or pulls back a factor of phi from here, and when it pulls back a factor of phi from here, we get phi 4k plus 1 here, and the job of this derivative is now over. So, what we are left with is integral of phi 4k plus 1 exponential of this term. Now, if you look at this carefully, this is again nothing but the phi but the 4k plus 1th moment of a Gaussian distribution. The whole thing can be converted to a Gaussian distribution by the usual process of completing the square, and you get this extra term outside, j square upon 2 mu, which can be taken outside the integral, and whatever remains inside is nothing but the odd moment, or the 4k plus 1th moment of a Gaussian distribution, which will happen to be 0. Therefore, and indeed this is 0 for every value of k. Why? Because for every value of k we get a odd movement. For every value of k we get the odd movement, and therefore, for every value of k this integral will vanish, and the net result is that the first derivative is equal to 0, and therefore the 1 point green function of this theory turns out to be 0. This is all the working of the theory, working of the calculations, how we have worked out or simplified this calculation. As I mentioned, we can take this outside the integral, because there is no phi involved in this. You take this term outside this integral. Inside this integral, what we have, it is the phi 4k plus 1th moment, and for every value of k this happens to be an odd moment. For every integral value of k this happens to be an odd moment, and therefore, for all the k's that are covered by the summation here, this integral will carry a 0 value, and therefore, this whole summation will be a summation of zeros resulting in 0, and the whole thing will vanish. Now, let us look at this second 2 point function. Let us look at, for a 2 point function, we need to do a second derivative of z interaction with respect to j, second derivative. Now, the first derivative we have already done. When we do the second derivative in this, the derivative operator will again operate on the j inside the integral, and will pull back another factor of phi. That means the phi inside the integral will have the power of 4k plus 2. Now, that is even. Therefore, it will not vanish. We make a, let us call this integral, the whole term under the integral, let us call it I. Now, we have to simplify this. To simplify this, what we do is we substitute z equal to phi minus j upon mu upon under root 1 upon mu. When you do the substitution, the factor I, remember I is only the integral part, it is not this entire part, it is not the entire value of g2, it is only the value of the integral. So, you make the substitution z equal to phi minus j upon mu upon under root 1 upon mu, and we get this expression, and this now translates, the exponential term within the integral translates to minus 1 by 2 z square dz. Please note, this is the standard normal distribution PDF, of course, subject to normalization. And let us look at the expression in the green box. This is interesting. When we look at the expression in the green box, when we expand it as a binomial series or a binomial series, what we get is the expression summation 4k plus 2 c I, this is NCR combination, z to the power I, j to the power this whole expression. Now, and this is summation from I equal to 0 to 4k plus 2. The important thing is that every term in this summation will contain a factor of j. In this summation, every term will contain a factor of j, except the one factor, one term where we have z is equal, where z has the power 4k plus 2. Z has the power 4k plus 2, all other terms will have some factor of j, and sum of z some power and j some power with other values of under root 1 upon mu, of course. But the point is, when I put j equal to 0 here, because ultimately my objective is to put j equal to 0 in this expression. When I put j equal to 0, all the terms will vanish except that one term which has z to the power 4 k plus 2 j to the power 0, which will be 1. Okay. In other words, the summation will give me just the one term, which is 4 k to the power 4 k plus 2 c 4 k plus 2, that is equal to 1 z to the power 4 k plus 2. So, the net result of this whole summation, when I substitute j equal to 0, will be this expression z to the power 4 k plus 2 e minus 1 by 2 z. This is the 4 k plus 2th moment of a normal distribution with a normalization, of course, and this on simplification, taking care of the various normalizations, I get the expression in the green box. To repeat, this is the 4 k plus 2th moment of a standard normal distribution, which is given by 4 k plus 2 factorial 2 to the power 2 k plus 1, 2 k plus 1 factorial, of course, with normalization, and when all those normalizations are taken care of, I get the expression in the green box. Putting this value of I in the original expression, what I get is the expression in the green box. So, this is the expression for G2, the general expression for G2. This is what I get for G2, and working similarly, you can get an expression for G to the power G2n as by this is G2, and working similarly we can get an expression for G2n, and putting the normalization back also, we can write G2n as H2n upon H0, where H0 is in a sense a factor connected with the normalization with the cancellation of this 2 pi upon mu factor, which is common to both the numerator and the denominator. The rest of the term in the denominator is H0, the rest of the term in the numerator is H2n, and the expression for the green functions where G2n is equal to H2n upon H0 is obtained by this expression, and when you expand them, you get these expressions for H0 and 1 upon H0. These are the normalization point issues where u is equal to 1 upon mu squared. Therefore, this gives us G0 is equal to 1, G2 is equal to this whole expression, equation number 1 I say, G4 is equal to equation number 2, G6 is equation number 3, and so on. And the connected green functions can be evaluated just in the way we have done earlier, and we get these expressions for the connected green functions C2, C4 and C6. This can be obtained directly from the generating functional of the connected green functions, which is nothing but the logarithm of the generating functional for the original green function. So, let us summarize what we have done quickly. The free theory is first of all, this slide gives us the basic terminology in a nutshell. The probability is given by n exponential minus S5, where S is the action. Normalization is done in this way in the equation shown on the top right hand of your slide. The n point green functions are defined as the moments of the distribution. Zj, the generating function of the green function, is given by introducing a source j, and then Gn is obtained by taking derivatives with respect to j of Zj, and then putting j equal to 0. The generating function for the connected green function again by log of Zj, this expression, and the field function is given by the derivative of the generating functional of the connected green functions. So, this was the terminology for the free field. We have a very simple Gaussian action, S phi is equal to 1 by 2 mu phi square, and the rest of the terms have been evaluated. In this case, of course, we can get closed form solutions of all the relevant terms of all the relevant parameters. It's quite straightforward, simply Gaussian integration. In the phi 4 model, we have a little bit of we introduce perturbation, the concept of perturbation, the procedure of perturbation, and making use of the perturbation we work out the various parameters of interest, we work out the normalization for the interaction theory, we work out the generating function for the interaction theory, and we work out the using the generating function for the interaction theory, we get the green functions for the endpoint. We worked out the 2-point green function explicitly. We have the expression for the endpoint green functions of the interaction theory. Then we have expressions for the connected green functions. Now, that is basically the main composition or the main part or the explicit part of the 0-dimensional field theory or a field theory on a underlying space of 0 dimensions. Then there is an approach or there is a formalism, an extension of this formalism which is called the Schwinger-Dyson equations. The Schwinger-Dyson equation gives us the equations of motion, the dynamics of the green functions, and they describe the propagation and interaction of the fields in the theory. So, they provide a very attractive formalism of how we are how the field interactions develop and the field propagates in time. These system of equations are fundamental to any field theory, although they are somewhat complicated, but they are fundamental to the theory. That one of the reasons in fact of selection of this 0-dimensional field theory is to enable us to understand the utility of these kind of approaches. So, in the next lecture I propose to take up the Schwinger-Dyson equations. Thank you.